thinking back to the big picture of everything, you've discussed what is science as a whole, the numbers associated with science, and then you danced into the history of science to talk specifically about the history of the atom. So you can talk about the electron, so you can talk about how the electron behaves with other electrons around it. So that's kind of the progression of where you've gone to up to this point. And then eventually we'll do chemical reactions. We cannot do chemical, we could. I mean, it's in textbooks to do it. I think it's arguably, how do you take a carbon dioxide and do a chemical reaction with it on the board and not understand its geometric shape? So that's what we're trying to do now. We did beryllium difluoride. Maybe over the weekend you dabbled in some of these others. We'll kind of tweak them out, but we'll go a little bit faster than what we did last time. This is not the, if you will, this is not like a comprehensive list of things that we're going to talk about. It's more of, if you want to understand the picture of boron trifluoride, these things need to be considered simultaneously. So that's the difficult part of this, is there's a lot of little pieces that make the actual arrangement of a molecule exist. Do you have to know all of these? No, you legitimately could memorize it and be fine, because it's proven that carbon dioxide is linear and has a certain bond angle. You don't have to do this. But this is a better gauge if you just kind of pick and pluck, if you will. You know this, and you stick it there in that thought, and you're like, all right, what does that mean? So let's try to get through as much as we can. We're not going to get through nearly all of it. That's fine. Definitely not this today, and probably not even molecular orbitals, but we'll kind of dabble in the rest. All right, so big picture, beryllium is an essential atom. Fluorine is the bonding atom, because beryllium is the lesser electronegative atom, and it shows up the fewest number of times in the chemical formula. So chemical formula. Fluorine has 7 valence electrons. Beryllium has 2 valence electrons. It doesn't matter how I put the electrons around fluorine. Like in terms of, can I put 2 electrons here and 1 electron there? Okay, it doesn't matter, right? So arguably, I'll start trying to do it in a way that always positions the unpaired electron between 2 atoms. That way we could draw some sort of a chemical bond. Okay. Why should we not draw a chemical bond? This was Friday for beryllium difluoride.
Because the metal doesn't have this.
Okay. This is a metal. You have a non-metal situation, right? So that is an ionic compound, and ionic compounds are formed from the complete transfer of electron density. So fluorine wants the electron more than beryllium does, so beryllium's going to give it to fluorine to form 2 fluoride ions. So this now becomes a beryllium ion plus 2 fluoride ions that are now interacting together. And those are stabilized by those, what we call electrostatic forces of attraction. That just means opposites attract and likes repel. So if beryllium difluoride forms, in general what we said is consider the energies associated with those. I think we use sodium chloride or something like that to begin with initially, but this is ultimately what we're talking about. So beryllium and fluoride has maximum proximal distance, meaning they're perfectly positioned beside each other. I guess we should have gone here. We could get to 0 eventually. This would be like beryllium, and this would be like fluoride, and this is infinity here. So this is some sort of infinite distance away from fluoride. The energies are 0, they're completely removed from each other. You have 2 ions. And then here, this would be like, and legitimately, it'd be like beryllium's electron density is beginning to overlap with fluoride. They're too close together, so I'll just draw F on top of BE. So there's some best distance, lowest energy, most stable. As you begin to separate them, it raises the energy of the system, or as you begin to push them in towards each other, now the nuclei want to repel, and the other core electrons also want to repel. So that's getting into a few of these other concepts. We'll keep trying to tweak that as we go through here. What do we say about electron density? We could look at how the electron density is being distributed between 2 sides. Anytime you have 2 regions of electron density, what term do you give that? 2 regions of electron density. What name do we give that? Trigonoplanar, tetrahedral? Linear, right? And linear is when we say how many regions of electron density, that's the word linear whenever you see 2. The molecular geometry, so remember that was if you take a picture with your camera and your camera cannot see any of the atoms or ions, all it sees is regions where electrons are isolated. Then there's one region, two regions between there, that's linear. If instead you found the three-dimensional shape, so that's corresponding to the word molecular geometry. What does it actually look like in 3 dimensions? It doesn't see the electrons, it sees the arrangement of atoms. So is this still in a linear fashion if you only look at the atoms and not the electrons? Yes, that is. So that's also linear. And then here's where we develop our bond angle from there. So the bond angle of 180 corresponds to the molecular geometry of linear, and that arises from how the atoms actually look in 3 dimensions. Okay, so I think that was Friday. Let's go ahead and add on to this list. We'll try to cover all of the standard ones, at least. Let me throw in carbon dioxide. No, let me do carbon dioxide a little bit later. Let's do boron trifluoride. Okay, boron's the central atom because it's lesser electronegative. Fluorines can sit around the outside, that's fine. Is this a covalent compound or an ionic compound? Covalent or ion? Metal, non-metal, or 2 nonmetals together? 2 nonmetals, so that's covalent. So we do need to form some actual tangible bonds in between them. Fluorine has 7 valence electrons, right? Between, or fluorine, all halogens have 7 valence electrons. So we put in the 7. How many valence electrons for boron? Based on its position, 3. It's in group 3, so we have this. It's more stable to be together than it is to be apart, so you pair unpaired electrons. So we're going to connect those electrons. That represents that those are being shared equally or unequally between those atoms. And now let's check for the octet rule. So we need fluorine to look like neon, and we need boron to look like either helium or like neon. 2, 4, 6, how many are here? 8. Okay, so 2, 4, 6, 8. 2, 4, 6, 8, 2, 4, 6, 8. Okay, fluorine has a noble gas configuration. That's good. Boron only has 2, 4, 6 electrons. That's not good. Okay, in a moment, this is going to be wrong, so let me show you the wrong way. It is perfectly fine, however, to consider the thought process of, well, fluorine doesn't have to keep them for himself. He could actually end up sharing them with boron a little bit better. So you just move these down here and say, instead of keeping them, you share them. Does that change the number of valence electrons for fluorine that fluorine now has? Does it still have 8? So that's 8. But now boron picked up 2, 4, 6, 8. That looks like to be a win situation. And by all practical purposes, that's the right process. That's what you would want to do if you needed to achieve a noble gas configuration, but you couldn't add or remove any more electrons. So move things down. However, fluorine is the most electronegative atom on the periodic table and does not want to share those electrons with any atom. No atom. It will not share more than it has to. So it's actually more stable for boron to have less electrons in its outer shell than a noble gas configuration than it is to try and rip them from fluorine and make it share with them. And legitimately, that's like 2 kids fighting on a park for 1 ball that they both want. It's just easier for one kid to be like, okay, you play with it for a while, right? Versus, no, it's mine. And the other kid's like, no way, it's not your. Yeah, it's going to take a ton of energy to do that. Not that you guys ever would have done that, right, back in the day? Check the total number of valence electrons. We have 3, and we had 7 for each fluorine times 3, right? So 7 electrons times the 3 atoms that are there. So if we add all that up, we should have 24 valence electrons. So 8, 8, and 8 makes our 24 valence electrons, which is nice. So we haven't broken this aspect of valence Lewis dot structures. And now consider these bond angles in here. These are 120 degrees. How do we know that? What do you think? Yeah, it makes a complete circle, right? And in terms of the 3-dimensional shape, which one of those 2 theories up on top are used to tell us about how electrons orient themselves in 3 dimensions? So, VSEPR, the valence shell electron pair repulsion theory, right? So let's use this one. Okay. So you have this there's our boron. Our fluorines are right here on the sides. If these want to come together, then these pairs of electrons will begin to repel. So to keep them there, I have to provide energy. If they bend and flex back the other way, then these electrons are going to repel, so are these as well. So we're going to maximize the distance. Why would I not want to bring them this way in 3 dimensions, though? Is this angle getting larger or smaller with that one if I bring it forward? Don't overthink that. So this is 120. If I come here, we know that's less. If I go there, I know it's more, but that makes this angle less. But if I bring it forward, let me really bend it. Make it straight out. What would that be? This would be, if it's
90 degrees?
yeah, that would be 90, right? So if you keep bringing this guy forward, the angle's going from 120 to something that becomes tends towards the limit of 90 degrees, right? So it's definitely getting less. So that's an optimal maximum distance. When you have 1, 2, 3 regions of electron density, the electron pair geometry is called trigonal or trigonal. I've heard it said both ways, so I'm fine with that. Trigonal planar, so that means 3 regions of electron density. And then the molecular geometry, whenever you have 3 atoms that are bonding and there are 0 lone pairs. Okay, that's the key. If there are no lone pairs around the central atom, meaning you don't see any dots like this, right? If there are no lone pairs on the central atom, then and always the electron pair geometry will be the same words that you use here as well. So trigonal or trigonal planar, and then the bond angle is 120 degrees. Okay. All right, we will get some distortions here in a second. All right, questions on that one though? So you have linear and you have trigonal planar. So those are the 2 first fundamental shapes that might arise. Okay. And then do you know of any others? Can you think back to other lectures you've had in other classes? Linear, trigonal, planar, do you have any others?
There's like a lot.
There are a lot.
List.
Yeah, there's bent, tetrahedral, trigonal, pyramidal, etc. So let's do CH4. Here. Okay. This is methane, carbon tetrahydride. Carbon, just did it. Let me slow down. Okay. Carbon has 4 valence electrons around it. That doesn't fit well. As a question mark, and put this as a question mark for now because I don't want to talk about it necessarily. Carbon's electron configuration 1s2, 2s2, 2p2, right? If you're looking here at the 2p sublevel, it looks like you have this. If you're looking at the 2s sublevel, it looks like this. Now you have to ask the question of, whenever you form a chemical bond, you're going to be taking an electron from somewhere else and either transferring it completely or sharing it with another electron. So that means that here, you actually would bring in an electron from hydrogen and place it here and place it here. How many bonds did you just form? Don't overthink that. Every time you share electrons, you form a bond. 2. But this says we can form 4 bonds between each or 4 bonds with 4 different hydrogens. So not necessarily right now, but we're going to come up with a way. So this can just be a question mark for now in your notes. Take this electron and move it over here to this 2p sublevel. And if you do that, can you put a hydrogen here?
Yeah.
Yeah? And can you put a hydrogen here?
Yeah.
Yeah, this is called hybridization. Yeah, hybridization. I don't know. That's a lot of I's.
Can you definitely define that?
Yeah, hybridization is, in essence, when you actually think of something that's hybrid, it's a mixture, right? And you can use it, generally speaking, like that. Hybridization in chemistry legitimately means you're taking the s atomic orbital and the p atomic orbital and mixing them together to provide more options for bonding. And we'll get into more of that. I promise. We'll come back to that in a second. But what we've done is we've taken one of the s atomic orbitals. So this is called sp3 here. We've taken one of the s atomic orbitals and mixed it with 3 different p atomic orbitals to create an sp3 hybridized orbital. So it's not going to have the same energy. It's not even necessarily going to have the same shape as any of the S and P's, but allows this bonding to occur. In general chemistry, you never did that. I'd argue most of the time we teachers leave that out because it's a more difficult concept. So for now, if we just had to say, could carbon make 4 bonds? Based on its electron configuration, no, it can't. But based on the true chemistry, yes, then this hybridization allows. So we'll come back to that. It's more stable for atoms or to have electrons to be together than it is to be apart, pair unpaired electrons. Check for an octet rule. 2, 4, 6, 8 around carbon. Is it okay that hydrogen has 2
Yes,
around it?
because it's a duet.
Because it looks like a duet, which is helium in essence. Total number of valence electrons, make sure we haven't violated that. That's 4 for carbon. That's 1 for each hydrogen times 4 hydrogens. We have 8 electrons. Remember, we're try hard. Please try hard to get this to be an even number. It's not that it has to be. That's not science. It doesn't have to be. Here, we try to simplify our exceptions and try to make everything be 8. And that's carbon tetrahydride. Okay, when you have 1, 2, 3, 4 regions of electron density, the electron pair geometry is considered to be this word called tetrahedral. And that means 4 regions of electron density. If you have no lone pairs around the central atom, none, will the molecular geometry be the same name as the electron pair geometry? Is that true? No lone pairs around the central atom? Yeah, it's going to be the same name. So I think this is still one of the examples on your homework problems. Is it first page, couple down or something? Okay. So the molecular geometry then, it's going to have the same name. This is going to end up being tetrahedral as well. What's tetra mean?
4.
And hedral means faces. So 4 faces. Here's our 4-faced structure. If you can see this, when we say hedral, it literally means like take a piece of paper and stick it on each side, and that's considered to be a face. I'll just use my hand. This is one face. Notice it's a triangular face. Can you see that? So if you come up to this point, you can put a piece of paper here. That's 1. This is 2. This is 3. Where's 4?
No problem.
It's 4 here. And it doesn't matter how I orient that in 3 dimensions, so I always have 4 faces. Yeah. Okay, the bond angles here are not intuitive. They're really not. Meaning, even though you go like this, and the question would be like, oh, that looks like 120. No, I mean, definitely not 90 because we'd have to be right there. Maybe 120 should be there. But when you're repelling this way and you're also having to repel this way as well from these 2 electron densities, these bond angles come out to be 109.5 degrees. Yeah. And is the 0.5 important? It actually is, because all the bond angles are so close together, we'll keep that 0.5 distortion. All right, linear, trigonoplanar, tetrahedral. And then there's one other basic structure, and I'm going to kind of jump ahead here to give you the fundamental basics. Let's do SF6, sulfur hexafluoride. Sulfur is the central atom. Fluorine are the bonding atoms. Okay. So 6 regions of electron density around there. Fluorine has 7 valence electrons. So we can go ahead and put those in. For the rest of the year, after this unit, you never have to put these electrons in again. All the electrons on the bonding atoms. We'll assume that they have enough to make a noble gas configuration. Okay. All right, how many valence for sulfur?
6.
Okay. More stable to be together than it is to be apart. Paired, unpaired electrons. So in essence, all you're doing is this. You're taking sulfur with 3, 6 fluorines. Just draw a line in between each one. And then you can give enough electrons to fluorine to be a noble gas. So do the math there. 6 electrons, 6 times 7 is 42 electrons. We should have 48 showing. 8 times 1, 2, 3, 4, 5, 6 is 48. So we haven't violated the total number of electrons. That's possible. Check for an octet. 2, 4, 6, 8, around 40. So 8, 8, 8, 8, and 8. What about sulfur though?
It's got 12.
It's got 12. All right, now we got to look at, remember when we originally started, we said main block, it's good for main block. It really begins to break down in row 3 at phosphorus and sulfur. So we need to be able to achieve, at least at minimum, an equal number of valence electrons around sulfur. Meaning we don't want this to add up to be 11 for sulfur. 12, fine. 14, fine. 16, fine. 15, no. 13, no. So on. Let's at minimum look at what's happening with sulfur here. We have, I'll just do the 3s2, and then this would be 3p5, right? For the electron configuration. 4, sorry. 4? 1, 2, 3, 4, 4. All right, so there's 3s, here's the 3p. Okay. How many bonds does it look like sulfur could make? 2. Like it only has a position to put 2 electrons in there. That would be okay. That would be like something like this, H2S, where we had sulfur binding twice, and then we had these 2 lone pairs. Notice that this lone pair looks like it could be this, and this lone pair looks like it could be here. And then sulfur has a hydrogen atom binding here and a hydrogen binding there. That looks like that could be a reasonable thing. And that is, that's dihydrogen sulfide gas. Toxic, kills you eventually, miserably, makes you suffocate. Nasty flavor too. Never had it. Volcanoes, that's this. Yeah, you don't just go start breathing out of this volcano. But, however, in order for sulfur to create 6 bonds, do something. I haven't shown you, I've never told you, I've never even given you an illusion to what it could be. You have a guess at how we can make 6 bonds out of here. What do each of these electrons have to look like in order for 6 bonds to occur? You could lose them, but then that's fair, I like what you're saying, we could lose 2, but now we have 4.
Move them to other one.
Yeah, like what?
4s.
Okay, I like that thought process, that's higher in energy. Let's stay with the 3rd energy level, so all of these have 3. Can you think of a 3rd energy level we could share those with?
3D.
Yeah, there you go, 3D. So if we could take this and promote it to here, and we could do the same thing as well, right? So now we're gone here and we're gone here. So these have been moved. We keep these 1 behind. Now we can make 6 bonds. 1, 2, 3, 4, 5, 6. Is that okay? Yeah, because you're in the 3rd energy level and it doesn't require much energy to allow that process to occur. So simply put, phosphorus and sulfur are beginning to have those 3rd energy level D formations that you can move electrons into and start violating the octet rule. Yeah.
So would the electrons that it's sharing from the other atom, would it go into the orbitals that are already filled in 3D, or would it continue to go into different orbitals?
These 2 orbitals, is that what you're saying?
Yeah, would it go in the
Yeah.
two? Okay.
Yeah.
just make sure.
And then, again, we're going to talk hybridization, because that's the next element of this. This would be like sp3 hybridized. You'd hybridize with 3. An s orbital has hybridized with p, and it's also hybridized with d. This would be like, what the heck? sp3d2 hybridized? Yeah, that's how many atomic orbitals are mixing in this element. Here's octahedral. Notice we have sulfur in the middle, and then if you count your fluorides around there, you have 6, right? Octa means 8. So whenever we say, and there's no, let me step back, 8 regions of electron density is octahedral. Right, this is for sulfur here. And then if all of those are bonding and you have no lone pairs around the central atom, the name will be the same, so octahedral as well. The bond angles in an octahedral. All right, forget this guy for a moment. Just look at this square. You have 1, 2, 3, 4 angles, and those angles make a nice little circle, right? Or at least I can spin it on the axis to make a circle. So what are these angles? 90. And then what's this angle? That's 90. And if I add this guy back in, what's these? That's 90 as well. So everything is 90 degrees for octahedral in there. And that is predicted just based on geometric arrangements.
How did you get the 8 regions?
Yeah, absolutely. And then for, well, 6 atoms, but 8, octa, 8 faces. 8 faces.
Oh, Oh,
Yeah, so here's one here,
yeah.
this triangle, this is 2, this is 3, this is 4, and if you flip that around, you get 4 on the bottom side.
Is there a way to determine that without the model?
In front of you?
Do you just have to think about it, or is it
Um,
just
in terms of the faces, the name could give you 8 faces. In terms of the arrangement, sometimes, remember that 3-dimensional box I couldn't draw? Remember that the other day? The better representation 3-dimensionally, at least scientifically, is to do something like, let me position it so I can see it for a second. So they use dashes and wedges. These wedges mean they're coming out at you, so it's these two. You stick sulfur exactly in the board, let the board cut it in half. You use these dashes to symbolize things that are going back into the board. So these two would literally be going into Miss Lane's room, this one and this one, right? If I smash that in. And then is this atom in the same plane as this atom and this atom? Yep. So then you just do that like this. So geometrically, 3-dimensionally, inorganic chemists, organic chemists love this. Like you won't find a peer-reviewed paper without what's called dashes and wedge notation. So you could almost see that this could come up to this point. There's 1. These 2 in the back come up to a point. There's 2. These 2 come up. There's a point. These 2 come up. And that's all on the top, because this sulfur is on the bottom of the plane that's cutting the board. It'd be the same thing on the bottom. Dashes and wedges. Cool. All right, well, those are the basic shapes: linear, trigonal planar, tetrahedral, and octahedral. All the other shapes are based upon those. So that's why we start with those fundamentally. So let's try to tweak out some of the other ones. And there's a pattern that arises, so we'll try to pick up on that pattern as we go through them. So I'll just list out the ones we did have though. We had linear, which was 2, right? And that was 180 degrees. And then we had trigonal planar. Okay. All right. Let's deviate from those slightly. So let's do NH3. That's ammonia, nitrogen, essential atom. Hydrogens are the bonding atoms around there. Doesn't matter necessarily how you draw that around. Nitrogen has 5 valence electrons. Each hydrogen has 1 valence electron. It's more stable to be together than it is to be apart. So unpaired electrons. So NH3. So I often do it like this, just to kind of see. Officially, the dash wedge thing, it doesn't matter, you don't have to do it. One of these would be a wedge, one of them would be a dash, and one is in the same plane, but it doesn't matter, just draw 3 lines. If you have 1, 2, 3, 4 regions of electron density, what are you calling that electron pair geometry? That's tetra. If you look at the the second page of your handout, maybe? Like the actual second page. Yeah, this for this table here, that's what you're doing right now, is this as well. So we're saying if you had 4 regions of electron density and there was 1 lone pair around the central atom, what shape would you call it in 3 dimensions? And this is called trigonal pyramidal. Trigonal pyramidal. So notice this for a moment. If you have, this is tetrahedral, okay, that's the basic structure, 4 regions. If I take this top atom and I remove it, but I keep this as a lone pair of electrons, the one I'm holding on to, these lone pairs of electrons are no longer stabilized by another atom here, right? So this legitimately is like if Rachel and I hold on to a rope together, there's only a certain distance we can move the rope because she has the other end of it. But if she lets go, legitimately, I could swing that rope all the way around me, right? So the rope being electrons, you can move those electrons more freely, they're not isolated. So if at some moment these electrons move this way, what's it do to this bond?
it pushes it down. And over here, it pushes down, etc. So what you end up getting is tetrahedral original arrangement, but these bonds, and I'll distort them a lot, are actually way far down, right? Bent almost like a rocket shape. So you have a triangular base, right? Triangular base that comes up to a point, and that's a pyramid. So a triangular base into a pyramid, trigonal, pyramidal. The bond angle there, not intuitive either, 107.5 degrees. So tetrahedral, 109, trigonal pyramidal, 107.5. Water. If water did not have the following properties, your life on Earth legitimately would be horrible. I really do mean that. It really would be. 6 valence electrons around oxygen, 1, 2, 3, 4, 5, 6. Around hydrogen is 1 pair unpaired electrons with the hydrogen and oxygen. Check the octet, 2, 4, 6, 8 around oxygen, 2 electrons around each hydrogen. We're okay there, right? Okay, so we haven't violated anything to work through this. How many regions of electron density surrounding the central atom? 1. Keep going. Keep going. Keep going. There you go, stop. Tetrahedral, you're right. Yeah, right. It has 4 regions of electron density surrounding it. Now, the pattern. To go from tetrahedral to trigonal pyramidal, how many lone pairs were around the central atom? 1. To go from tetrahedral to bent, you need how many lone pairs around the central atom? 2. So notice, you still can start with the tetrahedral arrangement of electron pairs, and now you can end up being distorted in 3 dimensions, and that's called bent. So water is a bent molecule.
Is it just bent or is it tetrahedral?
Yeah, let's do that here. Let's try to answer that this way. So water, if this is originally tetrahedral, carbon, tetrahydrate, methane, remove 1, that's trigonal pyramidal. Remove a second atom. Now, you still have 1, 2, 3, 4 regions of electron density. Lone pair bonding atoms here. These electrons more free to move about. So as they move themselves this way, this bond angle really bends down even more, right? So this is bent. So tetrahedral electron pair geometry and bent molecular geometry. You can see some sort of a bent process here. So this bond angle is 104.5 for water. Without that bond angle, legitimately the hydrogen bonding that water does would not exist in our lives. Legitimately vaporized. Things would be vaporized or a solid structure, frozen. Okay. All right. Let's do PCl5. Phosphorus in the middle. How many valence electrons for phosphorus? Phosphorus has how many valence electrons? 5? Yep, it's in group 5. Good. 7 times 5 is 35 valence electrons total for chlorine. That gives us our 40 electrons. Good. Nothing so crazy. We know that we have to have 5 regions of electron density surrounding the central atom. So I'll just kind of throw them on there like this. Phosphorus has 1, 2, 3, 4, 5 valence. Chlorine, of course, has 7 valence electrons. Now we got a little problem again. Phosphorus is in group 3, row 3. It is a main block element, but it looks like it's getting ready to violate the octet rule. Meaning if it has to bond 5 times to chlorine, and each time it bonds, it has 2 electrons in the bond, how many valence electrons are around phosphorus? So if every time you bond to chlorine, you have 2 valence electrons, you're going to have 10 around phosphorus, right? So it's more stable to be together than it is to be apart. Pair unpaired electrons, like this. Now what do we do with these 2 that look like they're paired with phosphorus? The same thing we did with sulfur. We promote one of the electrons in the 3p to the 3d, and we take one of the electrons in the 3s and we promote it to the 3d as well. More to come on that when we talk hybridization. But here we are, counting 40. 8 times 1, 2, 3, 4, 5 is 40. And then we have 8 around chlorines, that's an octet, 2, 4, 6, 8, 10 around phosphorus. It's at least an even number, that's good. And that's, again, because we can violate the octet rule starting at row 3 with phosphorus and chlorine. Okay, regions of electron density, 1, 2, 3, 4, 5 regions of electron density. That's called trigonal bipyramidal. Bipyramidal. How many lone pairs are on the central atom? 0. So will this name be the same? Molecular geometry? Yep. If there's no differences, no lone pairs. So trigonal or trigonal bipyramidal. This is trigonal bipyramidal. If you want to put a star by this one, this is the one I forgot in my head. This is one of the major ones that we originally started with. So tetrahedral, octalinear are the basic shapes, including trigonal bipyramidal. I forgot to put that one in earlier. Everything else is legitimately derived from these. Okay. So here's trigonal bipyramidal. Notice that, what shape do you see here? Triangle. And that triangle comes up to a point. That's a pyramid. What's bi mean? 2. So if you do that once for the top, right? And you flip it over, you do it again for the bottom. So that's the bi, twice. So you have twice a triangular pyramid. That's mean shape there. What are the bond angles here? Keep going. There's 1, 2, 3 of those. 120, because you can rotate those on the axis, right? And those angles make a circle. Okay, so these are 120 at the location. What about here? That's 90 here. Is that 90? And these? 90. Yeah. So you have 90s and 120s. Okay. What about, just kind of as a thought experiment here, and then I'll give you some time to work. What if we did this? Take trigonal bipyramidal, and let's remove 1. Oh, these are called axial bonds. These are called equatorial bonds. What's equatorial mean? The equator, right? So if you're treating this as the Earth, if you will, the equator would be at the center. So you could bisect that as a plane, so equatorial. If I remove one of these axial bonds, let's see what shape might be presented. So if I take that and I hold it like this, do I get a certain shape? Like, man, well, you know, like when you're looking around, you're like, and you're looking online and like, does that meet any requirements? And you're like, oh, maybe if I don't move an axial one, what if I move an equatorial one? And you're like, oh, should I, you know, and you keep modeling it in your head, or even if you had one of these. If you remove one equatorial, you get this shape. It's a playground equipment. What's that? Yeah, teeter-totter seesaw. So this is called seesaw. So there are the legs of the seesaw, and if you put those on the ground, you seesaw back and forth. I'm not so worried about the bond angles, but just ask the general question, what are these bond angles? Are these now 120, less than or greater than 120? These angles here. Because these are free to move about. Less than. So as they move over here, it pushes these down, right? So less than 120, what about here? That can't be 90 anymore, right? Because that angle too has to be distorted. So it's more empirically derived. You don't need to know the bond angles, but that's seesaw, okay? So trigonal bipyramidal with 1 lone pair around the central atom produces seesaw. Okay. Yeah?
So if it's moving, why don't the other ones shift away?
They do. Yeah.
So it keeps its shape?
Yeah, that's the thought process, right? We need to deal with that. That question right there is perfect for when we start dealing with the hybridization in the molecular orbitals. So hold on to that thought, because the real image, to your point, is why do I say this electron could be over here pushing this bond angle down? When, to your point, we don't know where the electron is at. The electron could be anywhere. The sum net total of time that the electron spends is most of its time over here, somewhere, right? Because it has the most freedom over here to repel valence electrons. So it's all occurring simultaneously. These bonds are being distorted in both because it's acting like it's over here and it's acting like it's over there, so these are both distorted. It's acting like it's here on this side, so these are distorted as well. You get total distortion because we don't actually know where the electron is at. Yeah, that's a really good point. Okay, so if you have one lone pair around the central atom with an original trigonal bipyramidal shape, you get seesaw. Now watch, if I pull off a second equatorial atom, take a guess what shape that is.
Upside down.
It's a T. Did you say T?
No.
What'd you say?
Upside down.
Oh, I said a T. I just heard T in there. Yeah, it's a T shape. They just call this T-shaped here, legitimately, from molecular geometry, right? And if I remove, go back to trigonal bipyramidal, if I remove a third electron off of that equatorial position, what shape molecularly? Linear, yeah. So all those additional shapes that John said that they exist at the very beginning are all derived from just removing atoms and leaving lone pairs of electrons around there. So those are the possibilities for trigonal bipyramidal. Remove one, seesaw, remove two, T, remove three, you get linear shaped. Now do the same thing for octahedral. If I remove, let's say, one off of the axial position here, you get some distortion occurring here. What this looks like, what shape does that look like?
Square.
That's a square, right? And it goes up to a point. That's square pyramidal, if you have one pulled off of the axial. If I pull off, so that's octahedral, right? We pulled one off the axial. If I pull a second one off the axial, what shape? You get square and planar, square planar, right? Yeah, and those are your other distorted shapes that come up in your text quite a bit. So go with trigonal bipyramidal and start removing atoms, or go with octahedral and start pulling off one at a time, and you get all those additional shapes. Okay.
We need to know all those additional shapes.
Yeah.
You need
But
to
not
write-
the but not the bond angles though. So let's fill in your table. We'll go back to that page, second page. That one. So this one is what we're looking at here. So you have 3, 2, 0. Or sorry, we'll go from the top row down. 2, 2, 0. We got the linear. Next one down. If you have 3 bonding atoms and no lone pairs, how many total regions do you have? 3, okay. So if you have no lone pairs and you have 3 regions of electron density, you're still trigonal planar, right? Because you have no lone pairs. These words have to be the same whenever there are no lone pairs. That's what you're dealing with here. So you should find a row that says 4 regions, 0 lone pairs, 4 bonding, 6 regions. Did I say 8? I meant 6, I'm sorry. 6.
But it's still octahedral.
It's still octahedral. 6 regions of electron density. No lone pairs, all bonding. 2 regions of electron density, no lone pairs, all bonding. 3 regions of electron density, no lone pairs, all bonding, right? So everything from this line up, no lone pairs, except for the trigonal bipyramidal one. That should be up here somewhere.
Does that mean that the one we did earlier has 6 regions?
The sulfur hexafluoride, yeah, sorry.
So then,
So 6, that's my fault. 6 regions, not 8 regions. 8 cases, 6 regions. And then the branching off. If you do trigonal bipyramidal, okay. If that's your electron pair geometry, how do we say this? Let's say start with the electron pair geometry of trigonal bipyramidal, then it produces the molecular geometries of the following. So if you have no lone pairs around the central atom, it produces the trigonal bipyramidal, right? So let me clarify that. You start with this shape, but all of these are bonding, right? This one, all bonding, trigonal bipyramidal. If you remove one of those equatorial positions, what shape did we get then? If you leave this one. See the legs? Okay. This is a teeter-totter or seesaw. So if you have one lone pair, you get seesaw. And this is molecular geometries. If you remove a second electron off of that equatorial position, what do you get? This one,
T.
that's the T.
Is that just what they're called, like they're just called seesaw?
Yeah,
And-
just T-shaped, seesaw. One lone pair, two lone pairs, you get T-shaped. And if you remove that third equatorial one, what do you get? That's linear. Okay. And I guess for trigonal bipyramidal, we're removing equatorial. That might be helpful as a little guide, because octahedral, you're doing the opposite, you're removing the other ones. So octahedral here. If octahedral remove one axial, what do you get? There's our square, that's pyramid. So octahedral with no lone pairs is octahedral. Octahedral with one lone pair is square pyramidal. Octahedral with two lone pairs this is our square, what? Planar. Yep. And those bond angles are predictable, right? You could see those at 90s if that's a complete circle. Nice. All right, now to deal with Gloria's question. It's a good question. Let's do PO4, 3 minus. This is phosphate, hypophosphate. Sorry, I hear you. Check the trend. So anything in row 2 or halogens is O3 or O4? O3. Everything else, O4. So this is phosphates. Yeah. Okay. Phosphorus in the middle, oxygens around the outside. Phosphorus has 5 valence electrons. Oxygen has 6 valence electrons. Like this. More stable to be together than it is to be apart. Pair unpaired electrons. Now we have some big issues. This is unpaired. This is unpaired. That's unpaired. And that looks like it's bonding, or that's paired, but you have an unpaired oxygen? Like, what the heck is going on, right? All right, so same thing that we just did that we're going to get into, but you can move electrons from the 3s and 3p and promote them to the 3d. When you do so, you can pair these to create a double bond. And now, what does this mean, this -3? It gained 3 electrons from somewhere. We don't know where, but somewhere, some other atom has given 3. It is, yeah. So where are we going to add those? I'm going to mark them as big circles so you can keep track of them. Here, here, and here. Doesn't that make each of those oxygens stable in? Right? So this generally will look like P double bonded oxygen, like this. With, we put brackets around here to say that's a -3 charge overall. So actually scientists do put brackets and they say somewhere on there are 3 additional electrons. Personally, I like to kind of throw those negative charges in there so I can see them. I know they're on the oxygens, but you don't have to. Okay. is this oxygen chemically identical in properties as this oxygen is? Don't overthink that. Is oxygen oxygen? Yeah. So back to Gloria's question alluded to is why the double bond here versus the double bond there? Or why the double bond here versus here or here? Put in these double-sided arrows and actually do that. So you can walk through those steps like this. You can move that double bond around to multiple locations. I guess I should keep since we're introducing it, I'll just keep all the electrons in there. So I'm just putting my 8 electrons around each oxygen. And whenever I have a double bond, I can only put 2 lone pairs around that oxygen. So let's keep shifting the arrow. And then I think we can do it one more time. All right, these are called resonance structures. Resonance structures. For resonance, you have to have a multiple bond. So you have to have a double, triple bond. And you have to have chemically identical atoms. So you have to have the same type of atom. Okay, so let me step here for a second. Notice we have a double bond, and now we can actually move that double bond around. But we can only move the double bond around if this is oxygen and this is oxygen. If this were something like sulfur, is sulfur chemically identical to oxygen? No, not perfectly, right? Like one of those has a greater desire for the electron. And depending on who's further up the periodic table wants the electron more, so oxygen is going to keep that. But this oxygen could switch it here or here, unless, again, that's a totally different atom. Then no, it cannot switch that double bond to this position. So it does need to be exactly the same type of atom for resonance to occur. Okay. Resonance is when you're shifting the double bond around. Now, take all these images, they actually exist. These really do exist. We need to decide which one of these contributes the most to the overall structure. And that's kind of a weird way to say, take all 4 of these images and clap them into one, what do you actually see? So what is in common with each and every single one of these? What's in common? Give me one thing that's in common. That no matter which image you look at, you see that.
There's one double bond.
That's true. Keep going.
There's 3 oxygens with 1 bond.
Yes.
There's a bracket.
Yeah, no, I got you.
There's a bracket with
So-
a negative.
Okay, so what you see is you see 4 oxygens always. You always see the central atom of phosphorus, and you always see a single bond. There? Always? No matter which image you look at, even here, you have a single bond with another single bond. That makes a double bond, but you at least see one line going between each phosphorus and oxygen. I did hear somebody say you have brackets with a -3 charge, okay? What else is in common with every image? What else? No matter where you look, you always see it. Don't overthink it. Something to do with all the dots, right?
There's dots.
Yeah, you're right. There are 2 dots at every single location, 2 pairs of lone pairs at every single location, right? Doesn't matter where you look, you have at least 2, at least 2, at least 2, at least 2, and so on through the whole system. You always have 2 lone pairs on every atom. Now, here's the challenge. Now think about this very carefully. If you have one extra slice of pizza, that's this guy right here, and that pizza can be shared amongst 1, 2, 3, 4 different people, how much pizza does each person get? Yeah, how much? A quarter, right? Just my bond. No, it really is that simple. It legitimately is. You can share this bond at 1, 2, 3, 4 locations, so you need another fourth of a bond at each of these locations. How do you show that legitimately? You just go like this. You just add in these partial bonds, so dots. They're not electrons, so make sure you distinguish between your electrons and not. So this is called the resonance hybrid structure. So this is actually what phosphate looks like overall in its chemical identity, is that it has a 1 1/4 of a bond character. 1 1/4 bond. This is 1 1/4. This is 1 1/4. And same thing here at each of those moments. 1 1/4 bond character. If you were to take a snapshot, legitimately, just take a picture and it froze all the electrons at some spot, generally speaking, for the rest of the year, we will choose one of these resonance structures and draw that only, instead of trying to draw this. This is somewhat confusing. We just want a snapshot of where it goes. Now you take a guess. Maybe on your page you might, so when you're doing your molecular or Lewis dot structures, you do not have to draw these on yours. This is on the back side wherever you saw phosphate. So is this one as well. And so is this one as well. I'm going to be shorthanded at least so you have something to kind of compare and go off of. Carbonate is going to look like this if I shorthand it. Sulfate will look like this. And nitrate will look like this. Okay, resonance or no resonance?
Resonance.
Yep, double bond and all the atoms are the same. Here,
Resonance.
resonance. Here,
Resonance.
resonance. They all have resonance. For sure. Okay. And then what else? What other examples are on there? I think I covered, that touches all of them. Oh, the acetate, hydroxide. Yeah. Okay, acetate, C2, H3O2 minus. Can hydrogen ever be in the center? No, why not?
It's special.
It only has one electron. It can't have another bond here if it's already bonding this direction. So never the center. Could be the center, could be the center. Most of the time carbon is a central atom. If carbon can make 4 bonds, right? I'm just gonna list out the possibilities here. So maybe you wait to draw for a second. We could do this. Hydrogen combined once. We have 3 of those. Oxygen combined how many times? 2. So legitimately, this is kind of like a puzzle. Like take these components and try to stick them together somehow, and eventually you get something that looks like this. You get carbon with hydrogen bonds up this side, connected to another carbon, double bonded oxygen, and an oxygen out there as well. So this is acetate. If we got to the point where we got the structure. So if you puzzled it together, we would get there. The question wants to know, and you might have to draw a line through that row. It says for what's the molecular geometry, etc. Okay, look at this carbon. Why don't you call that carbon number 1? And if you just draw a line, because that's one central atom, right? And this is the second central atom. That's also in the center as well. How many regions of electron density around this central atom? 4. 1, 2, 3, 4. What's the electron pair geometry of 4? Tetrahedral. Are there any lone pairs around that atom? No. So what's the molecular geometry? That's tetrahedral as well. Right? So you have tetrahedral electron pair, tetrahedral molecular, 109.5 degree bond angles. Okay, what's the electron pair geometry here? Be careful here. Yep, trigonal planar. 1, 2, 3. What's the molecular geometry? Are there any lone pairs? Nope, so it's trigonal planar. And the bond angle, 120, right? So you have legitimately something that looks like a mark.
So is it both? Like, is it the name of both?
Yep.
Like together?
Yeah, you can just put a line through there and say each center has this molecular geometry. So here is, I don't have the other component on, but here's the tetrahedral, carbon, 3 hydrogen, 1, 2, 3 hydrogen. These electrons are sharing with this carbon, right? So like this, you can see our 2 oxygens there. So this is the shape in 3 dimensions, and it can rotate around, right, fly around, but we have that occurring. Just with a double bond at this position here, at that guy. Right. All right. I better stop. Yeah, we better stop. Because I think that gives you plenty to catch up on, right? Yeah. Any other ones?
Exact same.
We had a step
And
sheet.
you're gonna focus on the.
Did. I'm finding that. I'm finding that.
It's like, oh no, it wasn't recording.
Upstairs.
Oh my god, what?
I didn't record it.